And we move to the last presentation of the session. So it will be given by Mirko Mariotti about the BondMachine project. So Mirko holds a degree in physics from the University of Perugia, where he's been working since 2002 at the Department of Physics and Geology as a system engineer, responsible for the department's information and communication technology infrastructure. Additionally, he collaborates on software development for experiments and engages in ICT and computer science research and development. His best achievement is the BondMachine project, which he will present us today. And this project, in development since 2017, won the Ion Award at the Innovate FPGA 2018 contest by Terazik and Intel.
Thank you.
The floor is yours.
Thank you. Can you hear me? This works. Okay. So now I'm talking about this project. This is the brief outline of what I'll be talking about. First, I will introduce the project and the idea behind it. And then I will talk about some experiments that we are conducting using this framework to make some machine learning, I would add inference on FPGA, and to make some quantum computing simulation on FPGAs. And then other things like a conclusion. So let's start with the introduction. As you may have been done, probably every one of you have done it, it's a common practice to put processor inside an FPGA and use that processor to make something. Now we have RISC-V that is growing, and this kind of things making their way. And this is also the case of this project. We are building processors and put in FPGA. But we are taking a different approach. Instead of putting a static processor inside the FPGA, we want to try to put an heterogeneous multi-core in both the cores and the interconnection that is shaped on a computational problem. So we have a computational problem, and we want to shape something that computes that problem in an FPGA, and we have called it the BondMachine architecture layer. The idea is then to put this architecture layer inside an FPGA and gaining concurrency and specialization of the cores and the concurrency of the FPGA. And moreover, we want to shape these architectures starting from high-level objects that can be high-level sources or something like TensorFlow or other things that we will see in a moment. So, what is this project? This project is a software ecosystem, so it's software that's run on Linux that can generate architectures. These architectures maybe are composed of computing core, very, very small, and they can be hundreds of core inside a single architecture or even thousands. They are very, very small, and they have not to be the same type of core. They can have different structures, different. We will see what this means, and they can be connecting one another in customly shapes. And moreover, they can also share non-computational objects, something like memories or channels or things like that. So, to give you an idea, this is an example. This should be a BondMachine with 3 processors. The first processor, the processor 0, shares a memory with the processor 1. The processor 2 shares a channel. Let alone what the channel is not important. It shares something with the processor 1. The whole BondMachine has 2 inputs and 3 outputs. So this is an example of one of these machines. So, the computational unit within the BondMachine, we call that CP, connecting processor, is an object that has some register, a number of register. We can choose the size of the register. We can choose, we have some register that are specialized to make a communication among cores. Essentially, one core write the data and the other can read the data, or more can read the data. And they can pick, they can be built.
This one. If I switch it, try to use this. That's
Okay. Okay. Where was the? Okay. The instruction of the single CP can be picked from this list here, and we can compose the core with these instructions. It has a dedicated ROM and RAM, and it can take its program from both, or from one of from the ROM or from the RAM, or in hybrid mode, jumping from one to the other one. And about the shared object, I mentioned that there are these objects that can be shared among processors, and that, for example, they are data storage, message passing, synchronization, and to use this from inside the processor, special instruction has to be bring inside the core. But I'm not talking about this one for long, because we already lost much time. This is the implemented shared object so far. If you are interested, we can talk about it offline. But or see here if you want to see more about this object, these things. And then we start writing the software that handle this kind of thing. So this is the abstraction, the idea that we have of such an object, and then we build the software. We build a first object that we call processor builder. That is a software that can be used to assemble one single core, one single CPU, one single processor. Then we have another one that is called BondMachine builder that takes the cores and attach it together and attach it to the shared object. And then we have all a framework for simulate the whole machine. But in order to understand better, I forgot, before that, we also developed a set of makefiles to glue all together. So we can create a project directory, put the files on, and with our makefiles and with other tools like this one that we developed, we can make one of these objects and run it on a FPGA. And this is an example. So we have this command here, that is the command that creates a project. We are creating a project that is called example. We move inside. Now we start creating the first piece of assembly code. This code here is just the pointer is. I have to, okay. Okay. This code here just R0 is a register. We clear the register. It takes data from this, that is a shared object that we will see later how is attached here, and then write on this O0, that is the special output register to be connected to another processor. So, going over, with this command, we start creating a processor that has a register size of 8, that use 2 registers as one output, attach this instruction to the processor and save it everything in a JSON representation, use that assembly as code, and inform the CP that there will be a shared object that is a linear serial number generator with this seed. After we have done that, we make another one that is another core that read from any one of its input and writes to its output. So it basically does nothing, just read one input and write the things that they have read to the output, and build another processor, just like we done before. So let's start building a BondMachine. With this command, we create an empty BondMachine. We add the 2 processor. We add one output to the BondMachine, And then we start creating bonds among the output and the last processor output, and from the first processor output to the second processor input, obtaining, and add also the shared object, like this, obtaining things like that. So using these command lines, we can create these objects that test the program on each core, and that makes something. In this case, it takes numbers from the pseudo-random generator. It sends the number to the other core. The other core just read the number and write the number to the output of the BondMachine, the global output of the BondMachine, and they start doing this forever. So let's go on. Let's use this command to validate the project. No workflow could be identified because we have not put the file that gives the project the board and the other information it needs. And we can do it creating a file like this, a file called local mk, and the essential information in the source, that is the file that we created in the previous step, and the board. In this case, it's a nice fun, lattice size fun, a little stick from lattice. And also this is not working. Okay. Okay. And also, set, no, it's not working. Okay. And also this file here, IceFun maps JSON, has to be created. There are other things like board slow that make the board just slowing down to let us see the LEDs that will be the output of the object. So let's create the constraint file, this standard thing, and create this file here that says which part of the BondMachine are connected to which part of the FPGA. So this is a kind of constraint file for the BondMachine. And in the end, we can validate the project, we can apply the project, and then with make BondMachine, we create the BondMachine in its final form. With make HDL, the system create the HDL for this object and bring it inside the working directory. And finally, we can make the project that creates a project with a given toolchain that is, in this case, is iStorm. And then make synthesis, make design, make implementation, and make by bitstream, create the bitstream. And finally, with the make program, the bitstream is programmed to the FPGA if the FPGA is attached to the system. So this is a complete example for that board. So clearly, this is a way that is not particularly friendly because we have manually to create things. But the idea is another. We can create, we can have other object, and we developed this object that creates the architecture for us. In particular, we can use a compiler to create the architecture in assembler, or we developed things that create this architecture starting from a trained neural network, or from a set of quantum gates. So let's see some of these examples. The first one, and probably the most interesting, is the compiler, that as any other compiler do things like this. Start from an high language source that in this case is Go, the Go programming languages, assemble a file and create the machine code. But this compiler makes something different. It starts compiling the program, create the assembly file, and while he's creating the assembly file, he also collects things that that are needed to create the architecture. So it creates the assembly file and starts creating the architecture. Create the machine code and the object in form HDL that will run that machine code. And in the end, that code can run on that implementation. This is a simple case. We can also have, this is an example, a working example, starting from this code. This is the invocation of the compiler. The compiler creates two things. Creates the assembly code and create the JSON representation that on the previous example I created manually. this JSON representation can be converted into HDL code and used to create the processor inside the FPGA, and the assembly can be compiled in a binary that can run on that FPGA. We can also do multi-core things, starting from different Go subroutine, Go routine, it's called Go routine. The compiler will create different cores. And inside the routine, we can make object specific to the BondGo compiler that can bind the routine one another. I don't go into detail here, but the result of that will be something like this. So this is one of the most important results. We put an architecture inside an FPGA, but the architecture is not a static one. It's also generated from the compilation project. There's another tool that is somewhat complementary to the BondGo compiler that is called BASM. It is the assembler, and it works with code fragments. You can take a fragment in assembly. That fragment in assembly can be used to generate a core. Quindi take this up, you can ask BASM to generate a core from the fragment, or you can take fragments and compose them, for example, sequentially or in other ways, and then put on cores the composed fragment. So you can create a structure of fragments and then assign pieces of this structure to different cores. And the system creates all the one machine with all the abstraction and attach all the cores. There is also support for template-based assembly code. This is a thing that has no way of existing in a static processor. For example, we can take a fragment of code and we can use a template to specify which multiply operation you use. And from at the beginning, this is a template, and then we can populate the template, resulting in a different implementation of the operation of multiplication, for example. So we can make, for example, a full neural network, and then we can change all the operation in another precision. Okay, this is things that I cannot talk about. And in the end, this fragment of assembly are a way to build, are building blocks for more complex machines. And this is what we used to start playing with machine learning object, machine learning inference. We started from the creation of, we created a tool called Neural Bond. And the idea is that, the idea is we have a library for neurons written in assembly, and this tool takes all this assembly, it maps one-on-one the neuron from the trained network of TensorFlow to the with the neurons in the library, and in the end it produces a neural network in the form of BondMachine with connecting processor. With this command, this is an example. We have a TensorFlow ret, and with this command here, take the trained neural network, the path of neurons, creates the BASM file, and BASM start collecting neurons from its base, from its library, and build things like this. Things like this. That is our neural network inside the FPGA. And finally, we can put the FPGA, the firmware on the FPGA. We have this framework, and we start playing around with numerical precisions. So we start taking a model, changing precisions. We start swapping functions from directly in hardware or building it in software. We can swap things easily, and we are trying to make a analysis of power consumption, occupancy on the FPGA, latency, and all the things that you usually are doing with an FPGA in these fields. And we try with experiment with these objects here. The other topic that in the last month we are trying to do is some quantum computing with FPGA with a similar approach. We have written a simulator that is called BMQSim. It takes a QASM similar code. I don't know how many of you have ever seen a quantum computer in action, but this is substantially a program for a quantum computer. This simulator takes the program and converts it into matrices, and then the matrices are placed inside CP, like this. So if you take with this approach, you take the gates became matrices, and inside the single CP, you have all the gates in the form of the operation that are done within this gate, and these are all done in parallel within the FPGA. So in the end, I don't go into details here. So in the end, we take with this object, we compare it with the standard quantum simulator like this, like Penninot or Qiskit, and we compare it to make sure that the results was the same. And this is an example of the algorithm of quantum teleportation done on FPGA. So just like the other one, create an example. This is the program, the quantum teleportation. This is the local MK file that describes the project, and this is the important things is the board. This in this case is an Alveo, and this is the source, the quantum program source. This is the quantum app, that is the app that we run on the host side. Other things. This is the information about the connection from the host to the FPGA, and the important thing is the axis stream interface here. And then there are the information about how to deploy the program on the host side, and then validate the program, apply the program, make the BondMachine and the HDL, wait some hour, and then you have to deploy the XCL bin for the FPGA, and in the end, you can run the simulation in software and then run the simulation in hardware, having the same result. Other things about this project, so in the end in the end, we have this way of creating this architecture. We can use these architectures in several ways. We have 3D printed a case, touch the monitor, and use it one of these as a standard computer with its own limitation. Or we tried experimenting deploying this architecture on multiple FPGA. Or we can use the produces architecture as accelerator for standard payloads, like the quantum teleportation case. This is the project timeline. As we said before, the major achievement was the grand final at Intel campus in 2018. And then this is the board that currently are supported. I won't say supported, I just say the board where once has run a BondMachine, because this is not a big project in terms of effort. Now we are doing the accelerator part on Xilinx and on the Alveo U50C, with the idea of going to the National Supercomputing Center in Italy, that will have FPGA cluster, especially for the part of clustering. This is some reference if you are interested. There's an organization in GitHub that is this one. This is the main repo with the source file and some working example here. And this is the paper that describes in some detail all the architecture. So concluding, all the ecosystem in a nutshell is things like that. We have this abstraction and several ways to create this abstraction. We can operate changes directly on the abstraction without using an FPGA. For example, we can change numerical precision, make optimization to software, hardware inside the abstraction. We can change instruction. We can change data types. Or we can change the structure of the connection on the machine, and then we can use this machine in one of these way and on different fabrics. So it's a sort of layer, a computational layer built on top of generic FPGA that can be used to make some computation. If you want a similarity, you can think of LLVM, that is a layer that has several backends that are different architectures, and compiler that compile for the LLVM IR, for the intermediate representation. This is something similar but done in hardware, with the idea of having a computing abstraction. Okay, thank you.
Thank you, Mirko, for this complete presentation and amazing work. Any question for Mirko? Yeah. 2 questions.
Thank you. Very impressive. I have too many questions, sorry, but I'll try and keep it to just 2 that are slightly related. Would it be possible to put this on an ASIC?
I don't know. I guess so. I never tried.
And then the second question, would it be possible to make it radiation hard?
To make it?
Radiation hard.
Radiation hard. What does it mean, radiation hard?
It means you triplicate your circuit in order to avoid upsets by radiation. Okay, if you don't,
I don't know.
Okay, fine. Okay, thanks.
So, yeah, again, great work. So, I saw 2 use cases that you showed. One was a neural network one. Other was for quantum computing, right? But there are a lot of companies now who are into this RISC-V extensions thingy, right? So they have a RISC-V processor. For their own use case, they have some extensions. In this extension, some of it is this ASM magic and all that you do, right?
What extension?
RISC-V extension, RISC-V architecture and extension.
No, that was just an example. It has nothing to do with that.
Right, but I'm saying that can this be used as a tool to generate RISC-V extensions?
I was talking about it, yes. I was thinking about it, yes. But I never tried and never explored I explored the idea, but I never go into it.
There are companies that have a business around this model also, just for your information. Yeah.
I was planning to examine, to study RISC-V and see what it takes to make an extension and try to do something like that, yes.
Okay. So I think like it's possible, then that is what I think. It can be extended to in that direction.
Yeah.
Okay.
Yeah.
Thank you.
Yes, I have a question. So actually one of the 2 questions was also related to the instruction set extension of the RISC-V or many also other NIOS 2 or the microblades, for example, soft cores from the vendor's FPGA provider. But then the first question was, now you have this architecture that is sort of generic, and then you build up your customization, your hardware specialization. You still need to do some hardware design in VHDL or Verilog. Is that right?
Yes, it depends on the board, yes. Of course you do.
My question is, have you think about using HLS for doing automatically this translation from software to hardware?
We also are looking into it, yes. Yeah. But HLS is just Xilinx related, so no, yeah. Well, so
Are you here tomorrow? You will be here tomorrow. We can.
okay,
You can
okay.
about HLS.
Yes, but we are looking into it. The idea is to have an architecture and to play around with the architecture. I can even imagine reaching a quantum computer simulator when I first start thinking about it, but we reached it, so it's...
But the project is very exciting.
Thank you.
Congratulations.
Thank you. Just to... Is it audible? Okay.
Oh, okay.
Here, okay. Thanks for the presentation. Very nice effort indeed. And I think, it's quite kind of a question and statement. It's a project that actually tries to simplify the design and make it more streamlined, higher level, and so on. Although you said you just write HDL files, right? And interestingly enough, I think there is some similarity with the SOC make project that there is a term for ASICs, but I'm not sure it is the same level of organization. Just resembles to me. Maybe people who are more expert can comment. And the second part is about the QC and the quantum circuit that you implemented. Obviously, this is a demonstrator, right? So, okay. Yeah. And because we already know that these systems have a very high level of complexity and very large number of states, you used a quite powerful card. 55C?
No, right? For 3 qubits, we are doing it on a Z board.
Okay.
With an Alveo, we reach 4 qubit. We encounter big problem from 5 to... Right. Because 5 qubit is some sort of 2000 processors generated.
Okay, so...
I didn't go into details, but this version here creates the full matrices, not regarding the entanglement state of the qubits. Okay. So we are thinking about taking into account also the entanglement state, and it will reduce the number of states if the bits are not entangled. So, but it's an ongoing work, and so.
Right, and obviously there is some gain expected in this computational effort. I mean, that's why you actually place it on this FPGA. It's not just a proof of concept. You would
on the quantum part, the gain is probably that if you reduce the precision, you can have much gates, much profundity, and you can maybe not lose so much. So you can change the precision, and on the computer you cannot change the precision.
So you gain also simulation flexibility. Okay.
That is the same gain that you have in neural networks. So the reasons that you are not using 32 bits on neural networks because you don't need it. So you can reduce the precision and have enough accuracy. You are okay, and you are way better than the computer.
Another, the last one.
Thank you. It was a very impressive topic. It's amazing. I was just wondering, do you have any comparison of this with respect to other tools that helped develop putting the neural nets in the FPGAs? For instance, I know HLS for ML.
Yes, we have comparison with HML for SL. Clearly, we build more abstraction, more structure, so we are not performant as HML for ML in machine learning. But the abstraction give us much control in similar way that you use your SPI buffers. So we have processor here inside, so we can make them do whatever we want. We are not just a kernel that runs on a phone. We have this data and this kind of comparison, but it's two different things.
So maybe I'm wrong, but maybe there will be a moment in which, if the resources of the FPGA will be much more with respect to what we have now, this can be expanded and can probably overtake what HLS4ML is doing.
I don't know.
This is just looking at the ball of glass.
So, it's fun also the idea that you have the same object and you just instantiate on two different FPGA on different vendors, but all the optimization is done prior going to FPGA. So if you had to do, as we said before, very fast things, you have to modify then the HDL. But in principle, you are enough general to go on several FPGA.
Okay, as someone brought out HLS4ML, I wanted to ask what tasks you benchmark you already beat HLS4ML?
Sorry?
On what kind of task you approach beats HLS4ML for like a significant margin?
You want to see the benchmark?
Like on what kind of task?
We tested power consumption, but I guess not against HML. Okay, maybe yes. We tested the latency on the same neural network built with the two differences. Okay. And if we are lucky, you're about to see this on a paper. We are waiting for review right now. So.
Is the paper open?
Sorry?
Is the paper open for access already, like on archive?
No, we don't put. We will put it there. Yeah.
Okay, now can I see any of the results? Because I'm on the HLS4ML side, and if that indicates some improvement can be done on our side, I'll be very interested in.
Okay.
Okay, thank you. Thank you, Mirko, again. And with this, we close the session. Thank you to all the speakers and for all of you.